for Energy Studies. Dr. Joel Swisher. Joel just started at Western this November. He took over from me as the director of the Institute for Energy Studies. He came from Stanford University, where he taught for many years, and he also has worked in the private industry doing consulting, and also in the nonprofit world with the Rocky Mountain Institute. And getting Joel to come here to take over this program was a huge coup for Western. So, Joel, please.
Thanks, Andy. Okay. Well, and the punchline to all of that is that all of the reason we have all of this wonderful energy curricula developing now is because of the leadership to date of Andy Bunn, and we all owe him a lot for getting us to this point, and then getting to go back to being a real professor again. So congratulations on that, and thank you again, Andy. So back when I was an undergraduate, energy was about this. There were actually shortages of fuel, and you had to line up at the station to get gasoline in your tank. And I was an undergraduate, and we didn't have an energy program, but we had one very visionary professor who offered classes in what we were calling alternative energy, which I was very interested in and took. The thing that was kind of indicative at the time was that the class wasn't called energy efficient buildings or small scale energy systems or renewable energy. It was called Designs for Alternative Lifestyles. I kid you not. The question was, are we going to run out? Is there enough energy supply, and in particular, petroleum? And I don't know why Nixon met Elvis, but I thought that was a good picture for the time. So today things have changed. We have a little bit different issues. All those questions of the cost of energy and pollution and so forth are still there, but climate change in particular, and you can make your own decision about the causes and impacts of Manhattan being underwater, but it is clearly one of the drivers of today's energy economy and driving our thinking. And our thinking has changed quite a bit since those days. I would say back at that time, when we thought about the energy system and analyzing it, from an academic or scientific perspective, it was pretty much this part of the picture, which I stole from Scientific American, that we had energy resources, we converted them, for example, petroleum refining or power generation, and we created our fuel or our electric power. And the challenge was, how do we get enough of those commodities to keep up with what we assume to be ever exponentially growing demand? And then, backing up to the supply chain, how could we tolerate and how could we mitigate the environmental consequences of that ever-growing supply to meet that ever-growing demand? And the only option we really were thinking about from a technical standpoint was, well, can we make the conversion process more efficient or cleaner? And in particular, can we use renewables? And at that point, the answer was pretty much, well, let's go do some research. So I did that. I went and worked at the Solar Energy Research Institute at the beginning of my career. But in the meantime, there was a paradigm change, and we started thinking about the energy system more as a system. And so we thought about the fact that what we really need is not gallons of fuel and kilowatt hours of electricity, but what we need is to move down the road, or at least to be at our destination. Maybe we don't even need the transportation if we think about it more holistically. Or we need to light the task that we're trying to do. That's why Thomas Edison invented the light bulb back in 1880, whatever it was, in New Jersey, so we could see when we otherwise couldn't, like at night. I'll have an interesting observation about that in a minute. But the other key observation that was made at that time that was really rather heretical was that there's technology here on the demand side. And the technologies that we use to convert fuel to transport, that is our vehicles and our transport systems, the technology here to convert electricity into illumination has its own performance, its own cost, and its own efficiency. And we can use technology and our know-how, which is more like a renewable resource, to improve that performance and provide more of the stuff we want with not as much, maybe even a diminishing amount of all this supply that is leading to those environmental consequences that we don't want. The idea of energy efficiency as a resource really came out of that time. And as I said, it was very controversial at the time. I think it's become much more accepted, but certainly not universally applied. So, okay, I'm a card-carrying engineer. I have to have one equation for you all. And I just want to point out from sort of the accounting or scientific standpoint how this all sort of fits together in a framework. If we're talking about mitigating our CO2 emissions, well, we got to figure out what are those emissions. And typically in an energy chain, the CO2 emissions can simply be measured by the identity. It's the energy use times the carbon intensity, the CO2 emissions embodied in that energy carrier. And that's pretty straightforward to figure out. If we look at the energy use itself, thinking back to the previous slide and the fact that we're trying to provide a service, that's what we're really after as the consumer, and meeting that service with some kind of efficiency defined in whatever units are appropriate, whether it's lumens of light or miles of travel or ton miles of freight, what have you. But the energy use is proportional to the amount of energy services, the more service, the more use, divided by the efficiency with which it's provided on the demand side, on the end use side. Meanwhile, the carbon intensity is proportional to the carbon content of the fuel that we're using. So for coal, that's the high number. For natural gas, it's a lower number. For renewable energy, it's close to zero, or identically to zero, depending on your definition, divided by the efficiency with which we use that fuel. The more efficiently we use it, the less carbon intensive the energy carrier. Now, so for the scientific sticklers here, you look at those units and say, wait a minute, that's silly. You've got equivalent units there. That could be dimensionless. Kilowatt hours and gigajoules are indeed both energy units. And you're right. I just left it in that form to distinguish that I meant the kilowatt hours were the end use energy provided, and the gigajoules were the resource energy units going in. And of course, yes, if you were calculating the actual numbers, you'd align the units and get the numbers right. But the reason we do this sort of carbon accounting stuff, and you know, there's a lot of work to be done, whether it's on a campus or in a company or at a national level to say what are the emissions, is it does two things. One is we want to know what the emissions are, and if we're a regulated entity, we probably have to report them to some environmental body. But also, your emissions accounting becomes your roadmap. It says dig here. It shows you where the big items are and what sorts of opportunities might arise to mitigate your emissions, to reduce emissions, and hopefully to reduce costs at the same time. So if we look at each of the terms in those equations and we put them together, we see that our emissions are proportional to, of course, our energy services, the carbon content of the fuel that we use upstream to provide the energy, and then inversely proportional to the efficiency both on the supply side and the demand side. So we don't want to reduce energy services. I mean, we can if we want to try to sacrifice or conserve. But from the standpoint of the analysis of energy efficiency as a resource, we generally assume that the energy services are the same or even greater than originally expected, and that we're using technology to simply reduce the amount of energy or emissions required. But the other three terms in the equation indicate how we can reduce emissions. We look at the fuel carbon. Well, we can use lower carbon fuels, maybe renewables. We can look at the fuel efficiency, the rate of conversion, and figure out how to improve that. And finally, the other key term is the efficiency at the end use. And that's where the technology on the demand side, the idea of energy efficiency as a resource, comes into play. And that's really what we end up focusing on when we're trying to use energy efficiency as a resource wherever we use energy, whether it's in buildings, whether it's in transportation, whether it's in industry. So this simple kind of accounting framework, one provides a useful set of accounts, but it also provides the roadmap to say where can we improve performance and reduce emissions. Okay, I want to show you a couple slides looking at the very, very, very big picture, saying if we're concerned about climate change and we really want to look into the sort of mitigation that the scientists are telling us we need over the next 30 to 40 years to keep the temperature excursion at the Earth's surface within the 2 degrees C limit that's considered relatively safe, then we need to start figuring out that same question, which is what are the opportunities to reduce emissions compared to what they would be otherwise. So I'm going to show you the results from 2 published studies which both focus on California specifically, but I think the lessons apply pretty generally. So this is a paper from a Science article a couple years ago where they projected emissions going out to 2050, and you can see the upper line is the baseline emissions. That's the business as usual, which is, of course is always a matter of opinion and interpretation, and we can argue about how much improvement should be built into that. But that was their baseline. And then you can see each of the wedges of different colors there are different approaches to reducing emissions. And the authors are saying basically to meet a target of 80% reductions below the 1990 level, or 90% therefore below their baseline, you need all of these wedges. But what are the big ones? Well, the first one is a pretty substantial improvement in energy efficiency, driving down the demand for energy resources. And then the other really big one is decarbonizing electricity. What does that mean? Well, that means replacing fossil fuel sources. Well, it could be with lower carbon, but if you're reducing by 95%, it really means renewable energy to get to almost zero carbon electricity supply across the board. The other big line item comes from fuel switching in transportation. And transportation fuels can be switched to biofuels, but the big term in this equation is actually switching to electricity, electrifying transportation and to some degree stationary uses of fossil fuels that would otherwise emit CO2 directly, and by replacing them with electricity, not today's electricity, mind you, but that 95% decarbonized electricity, we get to almost a zero carbon energy supply in transportation that's very hard to do today. So the pillars of that strategy are the 3: efficiency, renewables, and electrification. Here's another study, and sorry that the graphics look a little bit different, but this is from Lawrence Berkeley National Lab, another more recently published study. And again, they have, for 2050, they have their baseline. It's a little bit different from the other one, but the same ballpark. And their big ticket items for reducing emissions, again, big improvement in energy efficiency, another substantial wedge in low greenhouse gas electricity. And again, at this stage, it pretty much has to be renewable energy to achieve that, or it could be nuclear, or it could be fossil fuel if you capture the carbon and sequester it geologically. But generally, it's zero carbon electricity. And then the next 2 items are same as in the other study: electrification of building energy to some degree, heating buildings with heat pumps rather than electric heat pumps rather than with, say, gas furnaces. But then electrifying transportation, particularly light vehicles, cars that have a limited daily range. It's harder to do that with long-range trucks. And then a little bit of biofuels in there. So there's 2 studies that pretty much confirm, or at least agree, given their assumptions, that the sort of pillars of a low-carbon energy strategy, and those are for California, but it applies pretty generally, that the main pillars ought to be massive improvement in energy efficiency as a resource to shrink the whole footprint of the energy supply system, and then decarbonizing the electricity supply in particular, using generally renewable energy, including the renewable energy we already have, such as the hydropower here in the Northwest. And then electrification of direct uses of fossil fuel, in particular light vehicles, but also some in buildings and other vehicles. And then finally, once you've done that with the power grid, you have a whole different system. As you know, today, the power grid is generally treated as pretty much a radial single directional flow of energy where the supply system simply follows the load as it varies in time. But when you introduce enough renewables to have essentially zero carbon power, you have a lot of time-varying supply of electricity, trying to meet a time-varying load for electricity. And they're not varying in exactly the same way. And so you need a lot of intelligence in the grid and probably systems that capture the inherent storage of energy in things like plug-in vehicles, thermal mass of buildings, and perhaps dedicated storage in things like batteries as well, all to run a much smarter grid that matches time-varying supply with time-varying demand. And so I think you can see there's a lot of really challenging but exciting technical challenges for our power engineering friends. And one of the interesting things that our new EE majors will be looking forward to working on. So the idea of energy efficiency as a resource has really kind of matured over the last few decades, and in fact, in the power sector in the Northwest, it's probably one of the places where it's most effectively practiced. And the advantage of energy efficiency, and the reason to think of it as a resource, is that we find that the more we look at the available technology and we look at the way we waste energy in just about all of those uses, whether it's in buildings or vehicles or what have you, there's still a lot of potential to improve efficiency and reduce waste with everything from very advanced technology to just not doing dumb things like leaving buildings illuminated with no one in them. At the same time, efficiency appears to act kind of as a renewable resource. You know, you would tend to think that, oh, well, once we put in all the efficient light bulbs, then there's no more potential. But what we find is we keep finding even more efficient technology, or we keep finding new approaches through technology, through controls, through new business models to capture more efficiency. And when people like the Northwest utilities do their projections of the potential for energy efficiency, they tend to find that we've got just as much potential today as we thought we had 20 years ago, even though we've used a lot of the opportunities available then in the meantime. And when we define the resource for energy efficiency, we typically only define it in terms of the opportunities available that cost less than supplying energy. That is, it costs less to save than to buy. And if you want to pay more, you could probably find more potential, but we typically don't even study at that level. Finally, by avoiding the energy supply resources, we avoid pollution, and we tend to concentrate the expenditures and the investments in technology to a greater degree at the local level because we're not importing fuel resources from outside the local system. And so there's often an economic development advantage when you look at kind of the local view of efficiency. Okay, so where do these opportunities arise? This is just a breakdown of the U.S. CO2 emissions by overall economic sector. And what you see is that about 40% of our emissions come from buildings, commercial buildings, residential buildings. And that aligns with about 40% of our energy use goes into buildings, about 70% of our electricity. And then transportation is kind of the second biggest piece, and industry next. But there's really a lot of potential for mitigating emissions through energy efficiency in buildings. And a lot of that then affects the demand in the electric power sector. So when we look at efficiency, we often get this interesting effect. This is actually from analysis of internal combustion engine vehicles, so the transportation sector. But it applies in other ways in buildings and in industry. So if we start with the energy input to the vehicle, that's the chemical energy in the fuel, and it's burned in the cylinders of the engine. We have generally about 62% on average losses from just the thermodynamic loss of converting that thermal energy from burning the fuel into work. So we're left with about 38% of our energy going into the drivetrain, but then a lot of that energy is lost due to mechanical losses of friction and other causes in the drivetrain. A little bit goes to accessory loads, you know, like my first car that had all the accessories, you know, a heater and an AM radio. But no, see, here's the thing. In the 70s, AM radio gave the best music you've ever heard, you know. So, you know, we had the music. You guys had the technology. We had the music. Anyway, So you only get about 15% of that original energy once you get to the wheels. And then what are the wheels driving? Well, most of that energy is overcoming aerodynamic drag, pushing the air out of the way. And the power of the aerodynamic drag goes up with the cube of your speed, and the amount of energy required, therefore, goes up with the square of speed. And then rolling resistance, the friction that you need to move the wheels down the road. If you don't have any friction, you're in trouble, right? So that's not a completely avoidable loss. And so now we're down to about 5% of the original energy goes to the kinetic energy of the vehicle moving down the road. And how much of that is moving you? Well, not much, because it's proportional to the weight, and you're only a small fraction of the weight of the total vehicle. So probably less than 1% of the original 100% of energy in the fuel goes to moving you and your groceries, the payload. And that's after 100 years of automotive engineering. It's kind of depressing. But the point here is simply that, you know, we continue to work on the efficiency of the drivetrain, and we've really improved that quite a bit, and every point of efficiency counts. But if we look back down at near the end of the energy chain, if we can reduce the weight and thereby reduce the need for that kinetic energy to be as great, if we can reduce the aero drag and the rolling resistance so we don't have to apply as much energy to the wheels, all of those savings multiply upstream. A few percentage saved down here turns into a much larger, multiplied, compounded energy savings, and has much greater leverage, greater effect, as much as 7 times in this example. And we find that a similar sort of thing in things like data centers, where maybe 1% of the electrical energy that's provided to a data center actually goes into useful computing, because of all the different inefficiencies which we've begun to figure out how to economize on. Also in energy in manufacturing, you find a whole energy chain like this that feeds into systems for electrical pumping and fluids handling that is involved in industrial process, and in industrial processes, and you get this compounding effect that if you can save 1 unit of energy at the actual point of end use, whether it's the vehicle load here, or whether it's the semiconductor tool in a semiconductor fab, any of those sorts of final energy uses translate into much bigger savings upstream, and so therefore have quite a bit of power and leverage. This is a little war story from a project when I was with Rocky Mountain Institute. We started a industrial consortium with a number of the tier 1 suppliers to the Detroit automakers, Johnson Controls, Alcoa, and then some IT firms like Google and others. And we did a clean sheet design. Really, let's design a vehicle that, assuming 21st century technology rather than 19th. And it was a lightweight, plug-in hybrid fleet vehicle, so like a delivery truck, utility van, very underserved market. We got some financing, set up shop near Indianapolis to go into production, and then they had some struggles. First, the financial crisis hit, and then they turned to the Department of Energy loan program, from which they were assured they would get loan guarantees that would carry them through until the confidence was restored to get more private financing. And then there was this kind of manufactured crisis around the failure of a solar company called Solyndra. Don't know if you remember that, but it pretty much shut down the DOE loan program, and unfortunately our colleagues in Bright Automotive failed. But the technology has been acquired by some of the other automakers, and that's hopeful, because I think this was a design project that actually really followed those principles of looking at the downstream energy use and trying to leverage that over the whole system. The same thing applies with buildings. This was an example of an office building in North Dakota that our building energy team worked on. And what they found is that in order to improve the efficiency of the design of this new building, to achieve energy savings of about $50,000 a year, they had to spend more money on the components of the building. They get better windows. They used daylighting controls to basically enable the building to be illuminated naturally during the day and not use electric lighting. They had greater insulation, particularly in the roof. They had much more efficient electrical lighting systems. Spent about $125K total incremental cost above what the building was going to cost otherwise. But here's the thing. The improvement in the efficiency and the reduction in the thermal loads of the building enable them to greatly simplify and downsize the air conditioning equipment. And yes, you need air conditioning in a commercial building in North Dakota. And that caused a capital cost savings that completely offset the additional costs of the efficient components. So that our payback, rather than being maybe 2.5 years based on our energy savings, which wouldn't have been too bad, was actually immediate. And this is very much a best case scenario where we had total control over the building components. And it's also key that it was a new building. And when you have a new building or a new vehicle that you're designing, you have the opportunity to really nail the design with energy efficiency and future energy costs as an important part of your design and the performance that you're trying to achieve. It's much harder, it's doable, but it's harder and therefore generally more expensive to save energy in existing buildings or existing facilities of any sort. We have to do that because buildings in particular last a really long time. So retrofits will be part of an energy efficiency program, but it's always the hard part. It's the more difficult and expensive and frustrating part. So we can also use renewable energy in buildings. As I said, it was a huge contribution to society when we invented the light bulb, and we could thereby see when we otherwise couldn't, and do things like read and study and, I don't know, play baseball at night. But the funny thing is we actually use, of the 20% of our electricity that goes to lighting, most of it is used during the day when there's daylight and we can see. But we still burn electric lights. And we don't need to. We can design buildings to harness daylight, switch off those electric lights. You see a lot of well-daylit building where they do everything but switch off the electric lights, which is really frustrating. This is a school in Colorado that is nicely daylit. And again, in a new building, this is a pretty straightforward approach that can often have modest cost implications. In retrofit situations, daylighting is more challenging, but doable, and we're coming up with new technologies. Now, most of what I'm talking about is thinking about the US, and I'll think even more locally in a minute, but I do want to point out that in the grand scheme of things, a lot of future emissions are going to come from developing countries, particularly China. And you have to ask the question, well, is energy efficiency a resource there? And my take on that is there's no choice but to use energy efficiency as a resource, because every time there's a new building, vehicle, factory, what have you, in a situation like a fast-growing country such as China, it's a commitment to a lot of infrastructure that they're really having trouble keeping up with, and a lot of emissions and pollution that they're really having trouble managing. And one of the straightest paths to limiting the need for that new infrastructure and limiting the accumulation of those local emissions, not to mention greenhouse gases, is through energy efficiency. So one of the big challenges is to build efficiency into development planning and development economics right from the start. Okay. So meanwhile, I talked about efficiency, and renewables is the other plank in the low-carbon energy strategy. And unlike back when we were talking about designs for alternative lifestyles, renewable energy is a real maturing industry today. Wind power provides 4, maybe 5% of both U.S. and global electricity. Solar is creeping up on 1%. And we have both utility-scale large systems and also small building-scale systems. This is a picture of the Ivanpah solar power plant that makes concentrates solar energy to run a heat engine, a steam plant, out in the Nevada desert. 400 megawatts, so that's enough to power a city of 100,000 or so, about the size of Bellingham, maybe, all by concentrating solar power on those 3 towers that have collection points to drive a thermal cycle. It's pretty amazing technology. And obviously, this is the technology because it concentrates beam radiation. You really need to be in a very arid climate. And we're starting to see the effect of renewable energy. And finally, after many years of increasing the amount of our power generation that was coming from coal, that's actually declined just recently in the last few years at the expense of renewables and natural gas fired generation increasing. Now, if you combine the supply side and the demand side in one place, you can think about taking a building, and this is a environmental science building actually from Oberlin College in Ohio, and I'll talk more about Oberlin in a sec. But they wanted to have a net zero building, and the idea there is you have first a very efficient building, okay, reducing the overall footprint for energy supply, and then enough on-site production from rooftop photovoltaics to get a net zero energy bill. Now, that's not saying this is a self-sufficient building, like off the grid or something, because it's producing a surplus when the sun's really cooking, and it's drawing energy from the grid at night or other times when the solar resource is not as great as the load requires. But on balance, it's net zero. And this was part of a carbon neutral strategy for the campus that I'll talk a little bit more about in a sec. We also have now, today, bigger buildings. This is the Bullitt Foundation. One of our advisory board members, Dennis Hayes, who was actually my first boss at the Solar Energy Research Institute back in that other decade we were talking about. And he has procured the largest net zero energy building to date in Seattle. And it's also what they call a living building. It's self-sufficient in water as well. And it's 100% supplied by rooftop solar power. And again, it's net zero. So it's exporting solar energy some of the time and buying from the grid, which is a pretty clean grid being in the Northwest. But net, it is not consuming energy over the course of the year. So Western has a climate action plan. The first thing you do in a climate action plan is you say, what's my footprint? What's my inventory? And why do you do that? Because you want to know your emissions, and it's your footprint, it's your roadmap, right? So this is the 2007 inventory. I know they've done a more recent one, but this is the one that's in the current plan. And what you find typically when you do a carbon footprint for a campus is buildings dominate, either directly or indirectly. The steam plant, the electrical supply and losses, and even the refrigerants are all generally powering heating and cooling, lighting, and equipment in the buildings. So building energy efficiency is the key resource and the key strategy in the roadmap for reducing and even neutralizing carbon emissions from a campus perspective. Now, I haven't worked on the Western campus plan yet, but I did a carbon neutral campus plan back in 2001 for Oberlin College, the folks that I talked about a minute ago that built the Lewis Center there that was net zero. And so what we found, I think, is pretty universal now, that the approach to doing a carbon neutral plan is first thing you do is inventory the emissions, okay? And again, that becomes the roadmap. Then you go out and look at the buildings, the existing buildings, and figure out what have you got, what is their actual energy performance, what are the opportunities, and you find out things about, like, what's the schedule for refurbishing those buildings or retrofitting equipment and replacing things and that kind of a thing. You figure out the capital plan, and then you simulate the building's performance with scenarios of improving efficiency through, remember, we're retrofitting now. This isn't the nice, easy job of new building design. This is the difficult job of figuring out retrofits that can be installed in existing buildings. And typically you do that to a sample, a subset of all the buildings, and kind of extrapolate your results to other like buildings. And then you look at the supply side. Is there a steam plant? In Oberlin's case, they had this old, dirty, coal-fired cogeneration plant that was actually due to be replaced eventually. And then you think about, well, if you're going to go carbon neutral, do you need to consider buying or even selling carbon offsets to net out your remaining emissions? And then you think about costs and financing. So we did that. And of course, we focused on where all of the footprint pointed, which was buildings, 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 and trying to improve energy efficiency in the heating space, the water heating, the lighting, air conditioning, plug loads, the computers, the laboratory hoods and all that sort of a thing. And then operating efficiency, what they call commissioning buildings, where we go and we actually instrument the buildings temporarily to figure out if the controls are actually doing what they're supposed to do. And what you find in commercial buildings and large buildings, no matter where you go, is that they don't. They don't work. There are controls glitches, I promise you, in every commercial building, everywhere. And the more you can track that and diagnose it and respond to it, you can improve energy efficiency really without any investment, just getting the thing to do what it's doing by design. And I can say that from experience, having worked in a lot of buildings. And today we're learning to automate all of that with new software and everything. And it's a really promising area of new energy efficiency resource. Again, making it that renewable resource that I postulated a little while ago. And then on top of all the efficiency stuff, we looked at this steam plant and the cogeneration system and thought a little bit about how to make that more efficient. Okay, so in figuring out strategies for reducing the campus emissions, you have to think about, are you going to be conservative? Are you going to be aggressive? Which direction are the costs going to push you and paybacks and so forth? And so we cooked up several scenarios of different approaches. The first was the baseline, like business as usual, don't do anything. That was just a reference. And then we had 3 action cases. And I came up with these, what I thought were really clever names. Don't ever do that. The administration just hated these names. Like it was hard to continue the conversation. But my names, which I thought were clever, were for the sort of easy, low-hanging fruit scenario. I called that the no-brainers scenario. For the more aggressive but still pretty practical scenario, the no regrets scenario. And for the really aggressive, try to get all the reductions through actions on campus, really push the envelope scenario, I call that the no prisoners scenario. The administration hated that. I don't know what I was thinking. I was trying to be so clever. I'm the consultant from up in the mountains in Colorado. And anyway, I think they still allow me in the state of Ohio, but that's about it. Okay, so anyway, that was the idea, is we looked at different strategies. And the observation was, look, if you want to be carbon neutral, you can do it any old time. Get out your checkbook. And you can offset your emissions by buying what are called renewable energy credits that are the renewable attribute of renewable generation, or by buying carbon offsets. Offsets are basically a contract to finance measures that will reduce emissions by a certain amount in a certain time with a certain degree of certainty. And of course, they vary in all of those things, particularly in the certainty. There are very ironclad offsets and there are very, very flimsy offsets. But the bottom line is there's supposed to be reductions that would not happen otherwise. And you can just go and buy offsets and say, hey, I'm carbon neutral. And some businesses do that. But that's not really the idea when you're on a campus. On the other hand, as you go through these scenarios, if it's getting really, really expensive to reduce emissions beyond a certain point, and you want to get to zero, well, maybe it's cheaper to buy the offsets for that difference. So in each scenario, what we found over time, so here's time and the emissions starting at about 50,000 in the baseline. And even in the baseline, there was some reduction. Just keeping up with standards would cause emissions to go down. And obviously, they weren't building many new buildings, but potentially, if they built all net zero, it wouldn't affect the emissions, although that would show up in the baseline. So they weren't building a lot. Okay. So the 3 scenarios reduced emissions at a different rate with different degrees of energy efficiency improvement. And then in each one, there was a big drop because they were going to take that old coal plant out back and shoot it and install a more efficient plant, or maybe switch to natural gas, or maybe even go to fuel cells or some more advanced technology. And then in the different scenarios, they got closer to zero, but only in the one scenario did they actually get to net zero emissions just by the actions on campus. So as I said, the offsets to get you down to zero could be offsets that you buy from something like carbon sequestration. They could be renewable energy credits, or just go out on the market and buy offsets from a hopefully credible and hopefully regulated source. The other idea we cooked up, though, that was kind of interesting, kind of exciting, was, well, now wait a minute. If we're producing and co-generating electricity on campus, providing power and heat and cooling all together at high efficiency using probably natural gas, it's a lot cleaner than the surrounding grid in Ohio, a lot of coal. And what if we produced surplus power, exported it for energy uses either in the grid or maybe electric vehicles replacing gasoline and reduced emissions in the community, and then said, hey, those are mine. I get credit. That's my offset. I own those reductions, not financially or legally, but from the standpoint of the emissions accounting. Sort of roll your own offsets. That was kind of the strategy that we cooked up for that no prisoners scenario, to try to get to net zero carbon without buying any offsets externally. So that was the idea. The other kind of interesting observation that we made is that time mattered a lot. And it wasn't a good idea to wait until the very end of the time horizon and say, oh my gosh, we got to reduce emissions to zero. But it also didn't make sense to blast all the reductions straight away and to try to force all the retrofits into those buildings. Rather, it made more sense to be a little more patient, a little more opportunistic, and think about, sooner or later, a lot of these buildings are going to be renovated. They're going to replace equipment. They're going to upgrade stuff. They're going to tear things out and put in new stuff. And that's when you try to nail the efficiency improvements and get the more bang for your buck, and maybe downsize the heating and cooling equipment like I talked about. And maybe by that time we'll have better technology. LED lighting will be that much cheaper, and so forth. And there were a whole lot of synergies that came from getting the timing of each investment just right. Not too fast, not too slow, and really following the capital investment plan of the university in order to do that. So that was kind of an interesting insight that we hadn't thought too much about. But when you have a time horizon for your emissions target, it really can help. Okay, so enough about Oberlin. Let's talk about Western. Sorry, this slide didn't get formatted very well. A little Mac Windows inconsistency. So the title of this slide is Teaching and Learning About Clean Energy at Western. So we're doing that now, thanks to Andy and colleagues and some of the people who are here, like Phil Thompson and I saw Mark Bassell from chemistry, who have been working really burning the midnight oil, I would say, on developing the curriculum for each of these new areas we have. We have an energy policy minor. I think some of you are probably enrolled in that, which really focuses on the economics and policy aspects of the energy system. We have the brand new energy science minor. I think Dave mentioned we'll have the new classes in that starting next year, a 200 level and 300 level, that'll dig deeper into the scientific toolkit of energy processes. We have we have an energy track in the new electrical engineering major, which will have one existing and two brand new electric power courses taught by one of our new faculty, Murad Abdelaziz. And we have brand new, ready to go, probably we'll have actual classes contributing to our BA in energy policy and management. Starting next year, we'll have a business of energy class. We'll have some new policy classes in addition to the one Tom is already doing. And we'll really combine business, economics, and policy analysis, I think, and provide a pretty nice toolkit for the graduates. So that's all in the works and happening, and we have faculty on board to teach classes for each of those. Our next aspirational step, which we don't have all the resources for yet, is to have a Bachelor of Science in Energy Science and Technology, which will build on the energy science curriculum that we're already putting in place. But from what you just heard, you can extrapolate that some of the key areas that we'll want to add capability are in energy efficiency and the building science that drives that, because buildings are such an important part of the energy efficiency potential, and also something where we can work right here on campus. We may not even need a new laboratory. The campus itself or the community around Bellingham might help provide us opportunities to study energy efficiency in buildings. Electric power systems, in addition to the real detailed analytics that our electrical engineering colleagues are doing, we want to look a little more broadly at electric system and electric utility resource planning. I think we can collaborate with our colleagues in economics and across the three schools that are involved in the energy the Institute for Energy Studies to look at the power system and treating energy efficiency as a resource. And I always think of the key question is, okay, that energy efficiency stuff is nice and renewables. At what point have you done enough of that with enough confidence that you don't build the coal plant or you don't build the natural gas plant. That's where the rubber hits the road. And we're doing that. We're doing that out in the field. And utilities are delaying and canceling fossil fuel plants. But you really have to work the numbers and to have confidence in the implementation of efficiency to make that happen. And so that's a process that we'll want to learn and have the students learn how to execute that. And we'll look at this idea of greenhouse gas management and mitigation. We'll want to do detailed footprint assessments. We'll want to do life cycle analysis, as Charlie's talking about. But we also want to use that as a roadmap to say, how do we mitigate emissions? And again, a campus going carbon neutral, maybe even going a little faster than the current plan suggests, might be a nice laboratory to test out and educate ourselves further about how each of those strategies can be deployed. So I look forward to working with all of you and learning from you as we try to do that thing. It'll be probably a lot of trial and error. I don't know if these are the right strategies, but we'll be discussing and hopefully refining them over the next few months, and hopefully have some of the classes for each of these minors and the major in place already in the next academic year, and hopefully building the BS classes upon those shortly thereafter. And it's all, of course, a function of resources from the state or from our private donors, and we'll be working hard to find those as well. So thanks for your attention and interest, and again, I look forward to working with all of you to execute this rather ambitious strategy. Any questions are welcome. Thanks.
We do have time for questions.
Okay, sorry, I ran out the clock a little bit there, but yeah. Yes?
I have a comment and a question. First of all, in your modeling, showing all these nice straight lines, I always get very suspicious of that, especially when you're talking to a reasonably sophisticated audience. We know it's not a line. There's uncertainty with that. And I immediately become suspicious when I don't see that uncertainty portrayed, because you're making lots of projections with many assumptions way into the future. So you know those lines aren't lines, but there's an error term about that. And so I always become suspicious of that. The second thing is, that's the comment. But the second thing is, what are you going to do about an economic displacing that's going to happen as you switch from coal and other kinds of carbon energy into these others? Because now the pushback about renewables and even fracking, believe it or not, is the fact that in Appalachia and so forth, there's an economic displacement that's occurring for lots of reasons. But what they're doing is blaming it on the fact that we're not supporting coal. And I think that's going to be a huge issue in transferring from one kind of economy to another, is that there are not all winners. Some people, at least for a short time, are losers. And how are you going to mitigate or manage that?
Okay, so quickly on the first question, obviously there's uncertainty in every one of the dozens of assumptions that go into those scenarios, and there's only 4 scenarios. There could be 400.
And 2 of them were pretty close.
What's that?
And 2 of the lines.
They were close, but they had a big difference qualitatively in terms of that. So that's why the 2 were on there. But the point is, it's not a prediction. Anything you say about the future is going to be wrong, I guarantee you, your prediction or mine. The idea is it's a model. We are very transparent about the assumptions. They drive those results. We have a range of scenarios that cover quite a wide range that come directly from those assumptions, and you dial one up or down, and you can see the result. It's just not very practical to show the full range of possibilities because it's literally infinite. And so again, it's a scenario. You know, it's not a projection.
We show the uncertainty all the time in certain scenarios.
Okay, well, this is not a risk assessment. It's just a background for devising a strategy and figuring out, why do you do modeling? Not for the numbers so much for the insights. What are the insights? Well, we came out with some interesting insights about the timing of investments that we hadn't thought about before, for example. We came up with some interesting insights about this idea of rolling your own offsets that we hadn't come about before. And those came from the numbers, and we could test those results by changing the numbers, and it's all transparent because what goes in the model we know is driving those results. So on economic impacts, every time fashion changes and long dresses go out of style and short dresses come into style, there's displacements. And every time any economic pattern changes, there's winners and losers. There's winners and losers every day, all the time, in everything. When we talk about an energy system transition, there will be winners and losers regardless of how it goes. We know that. We've seen that already. One of the things we do, one of the tools we tend to use in the analysis of energy planning is trying to get a handle on the net jobs. And what you find with energy efficiency, for example, is it tends to be pretty positive because typically the investments in energy savings drive more labor-intensive activities than the energy supplies that they replace. And because the energy efficiency measures are generally restricted to those that are considered cost-effective, they save money, they put money in the consumer's pocket, which when spent then generates additional employment. Now with renewable energy today, where we have to subsidize it, that's not so clear because that second part of that equation, we might actually be increasing costs. So it could go either way. So we can generally find that employment and certainly local content tends to increase with a clean energy strategy. But you're absolutely right. Of course, there's always winners and losers, as there are every day when every economic trend varies over time. And we certainly need policy measures to mitigate that for the losers, retraining and unemployment and all that sort of a thing. But you can't avoid it by picking one energy strategy over another. And so, I guess I wouldn't be willing to gamble on the planet's health to save some West Virginia coal miners' jobs. I mean, maybe we should just figure out a way to mitigate the impact in West Virginia and do a lot of other things to clean up the environment in West Virginia at the same time. So, back here?
I have a question about your last slide, that will, I think, draw on your expertise over decades. You have the missing piece.
That was kind of a cheap shot, I thought. I have a missing piece. Please, let's fill it in.
The missing piece you have here includes building energy efficiency.
Yes. Well, I'll tell you one missing piece already, vehicle efficiency.
Okay. Well, I studied that at C. Boulder before I finished high school.
You studied
that
building energy efficiency.
35 years ago.
Okay.
My question is,
You didn't stop by.
why doesn't that exist here and everywhere else across the country? Part of
Well,
the answer might be because the year after I did that, Gipper occupied the White House and everything got cut.
we're apolitical here. We're nonpartisan here.
Seriously, why isn't there a position like yours at every university, and why is that piece missing and not in place everywhere?
Honestly, I think I'll leave it to all of us to think about our political / social / institutional explanation for that. I can say that I've experienced the difficulty within the structure of academia to address these kinds of topics. And by the way, I did omit vehicle design because we do have great opportunities to work on vehicle design here as well. But, energy generally and energy efficiency very specifically tends to fall between the cracks in the traditional department and college structure and the silos that they create. And it's inherently interdisciplinary, and that's how we're trying to approach it. And that said, there's a big risk when you approach a topic in an interdisciplinary sense, is that you tend to be, and in most universities you very much are a second-class citizen. And when times get hard, as they inevitably do, and the resources shrink, everyone runs back into their original home department silos and waits it out. And in the meantime, the interdisciplinary enterprise wanes. And here at Western, and again, thanks to Andy and the other folks who have designed the program up until we have it today, we have tried to insulate our program from some of that. We have a stronger structure for the Institute so that hopefully our faculty remain loyal and dedicated to the energy studies work as much as they are in environmental science or chemistry or engineering or economics. but it's a real challenge. You know, the department structure was set up kind of in the post-war era when we were thinking about energy only as the left side of that diagram I showed at the beginning, and the energy efficiency enterprise, and even the kind of mixed up set of tools that you need to look at the energy system in general really don't fit all that well. And we're just now figuring out ways to do it. And even in the well-known programs like Energy and Resources at Berkeley, they struggle. And CU has a great building energy program, but they don't link it to other stuff very well in policy or utility planning. And I know people there. You know, I've lived in Boulder a long time, and you know, their academic administration just doesn't quite make it work. If they had, I might not be here.
I think we got to quit now because it is a class period to be able to leave. Joel can stick around, and if you have other things, you can come talk to him. Next week, we got a totally different thing going on. We got someone coming and talking about Western water laws and water resources. So, go Huxley.
All right.
Thanks, Joel.